Good evening, everyone. I welcome all the panelists, participants, today's speaker, Dr. Sangami sir. Hearty welcome you, sir, for this guest gathering. PSYP is a group of IEEE members and volunteers who have graduated from their first professional degree within the past 15 years. It is an international community whose members are interested in elevating their professional image, expanding their global network. PES student branch chapter of IEEE Swarnandhra student branch collaborating with PSYP hosting this webinar on the title of Small Wind Turbines. In this connection, I would like to invite Dr. Sangamesh sir for this title of this webinar. So, Mr. Balagan, please introduce today's speaker.
All right.
Mr. Balagan, please introduce today's speaker.
Okay, so with a great pleasure, I have the opportunity and privilege to introduce Dr. Sagamesh Kudapanaba. He's an assistant professor at Basafejwa Engineering College, renowned for his commitment to fostering academic excellence and driving innovation. Specializing in power and energy systems with a particular focus on wind power generation, he earned his PhD in electrical and electronic engineering from Visavaraya Technological University in Belgrade. A distinguished senior member of IEEE, Dr. Kudapanaba actively engages in various IEEE activities as an enthusiastic member and volunteer. His prolific research career is marked by notable achievements, securing research grants for projects such as the development and fabrication of BAWTG blades using natural fibers for domestic usage. With an impressive track record, he has obtained well over 5 lakhs in research grants from esteemed organizations, including KSCST, IIS Bangalore, IEEE Bangalore section, and so many more. Notably, he earned the coveted Best Researcher Mission 2020 Challenge Award in 2020. Driven by his passion for knowledge dissemination, Dr. Kudapanaba has authored numerous publications, delivered presentations at international conferences and journals, and has served as workshop speaker and facilitator since 2013. It's a great with great honor and privilege, I welcome Dr. Sangamesh to give his presentation. Thank you very much, Dr.
Thank you very much, Balagan, for a nice introduction of today's speaker. It's time to hear from Dr. Sangamesh sir on the title of Small Wind Turbines. The floor is yours, sir. Please.
So can I share it now, sir?
Yes, sir. Yes, sir. Yes, sir. Yes, sir. The screen is visible, sir.
Yes, sir.
Thank you.
So shall we start?
Yes, sir. You can continue, sir.
Yeah. Good evening, everyone. I'm Samesh Goratnava from Basaveshwara Engineering College, Bagalkote. I'm IEEE Day Ambassador, Exicom NKS, PESSP Student Branch Chapter Advisor. Today I'm presenting the small wind turbines in microgrid as even nowadays the requirement in the present community centers. So by looking into that perspective, so we'll move on to the small wind turbines in the community center distribution system, calling it as a microgrids. Installed capacity of distributed energy resources such as wind and solar photovoltaic is 43.7 gigawatt and 70 gigawatt in India respectively. Aggregate capacity of microgrids with distributed energy resources in India is 1.9 peak megawatt. Microgrid is a set of system having distributed energy resources supplying electricity to a connected loads and energy storage devices in distribution system. Community centers such as residential townships, educational institutes, government offices, military sectors, and so on have neatly laid on grid interactive distribution network. Solar photovoltaic and wind turbine generators are widely employed for localized generation in distribution system. Small wind turbine generators of the range 1 kilowatt to 5 kilowatt are more suitable for penetration in low tension side of the distribution system microgrids, particularly for low wind regimes. As per the Indian Grid Code and Karnataka State Electricity Regulatory Commission, voltage variation is allowed up to plus or minus 9% and plus or minus 6% for HT and LT respectively. Figure 1 describes about the typical single line diagram of microgrid architecture. Here that this microgrid architecture showing that starting from the 6 kilowatt main grid and step down to the 415 volt from the distribution transformer center. Further, at the 415 volt side, so we can call it as completely microgrid. Here that at the 415 volt side, in this diagram, it's showing that three radial feeders. Similarly, a number of feeders will be available in the typical practical distribution systems. In this particularly a single radial feeder, so we can able to see that one we can call it as circuit breakers. Then further we have sectionalized circuit breaker, microsource controllers, combined heat and power sources, heat loads. So like this, we can able to connect the loads and further the DERs also. So this microgrid architecture will help us to frame the existing distribution power system into the microgrids. Further, as for the title what we given for the small wind turbines in microgrid, here the figure 2 represent the schematic diagram of a small wind turbine generator connected to optimal phase in distribution system. Mainly, here you can able to see this is the grid or utility we can call, and this is three phase, three wire, and further after that, once if you have the 11 kV bar 415 volt distribution transformer centers, so it step down to the three phase 4 wire cables. So in three phase in India we can able to call it R, Y, B phases and one neutral wire. So in this three phase 4 wire, mainly there are single phase loads or even three phase loads also available. Mainly single phase loads, if we are able to connect, mainly we can call it as the simple residential home loads. And here in this example, it's showing that connecting the single phase loads mainly at the R and neutral phase. And similarly, you can able to see the three phase load. It can be connected to the all three phases and one neutral also. Similarly, as for the context here, the small wind turbine generator connected here, that is mainly is connected to the B phase and the neutral, because so the in the small wind turbine generator usually it having that small wind turbine generators only. That small wind turbine generator means it is the voltage capacity is about to generate around one from 10 volt to up to 110 volt variable three phase AC. Further, we are converting into that three phase variable AC into the constant DC. So has that some having the 12 volt constant DC or 24 volt constant DC, and then from further using the charge controllers and the inverters, so it is converting that constant DC into the constant single phase AC. That is in India 230 volt 50 hertz AC only. So that single phase AC is connected to this one of the phases here. Methodology here that we can call it mainly as for the impact of the small wind turbine generators in microgrid. So here that first of all we have to do that development and the approach for the representation of the distribution system, and then data collection and profiles of the small wind turbine generator and load profiles data. And here as this context, so BEC, that is Basaveshwar Engineering College, we have the SCADA for Distribution Automation Research Center, and there we are able to collect the data of the complete load and the small wind turbine generator. Then further aggregating and clustering of this small wind turbine generator and the bus loads. Then we can do the Monte Carlo simulation based upon this complete algorithm, that is mainly per penetration level and time series algorithm. Then allocation of this DER, mainly distributed energy resources, in this context is small wind turbine generator only. And then three-phase power flow analysis, means a three-phase power flow analysis, mainly the one we can call that forward backward algorithm, or even the this one now, as in using the open distribution system simulator. So that three-phase power flow analysis also applied. And by this one, so further we'll get the results and we'll do the impact assessments. Then modeling of small wind turbine generator. Figure 4 describe about the schematic diagram of wind turbine generator 4. That is here in wind turbine generators, we will show usually in the horizontal axis type of wind turbine generator. There are 4 types, that is a 1, 2, 3, 4, usually calling that 1 to 3 as a induction type generators. And 4 type is mainly for the permanent magnet synchronous generator. Here that the PMSG based small wind turbine generator in horizontal axis type 1, you basically using because of their advantages, mainly the advantages like a unified power flow controller. So using that one, so we'll get the unity power factor at the AC side of the wind turbine generator. So because of these advantages, so most of the small wind turbine generators used for the this at the three-phase side only. Then stochastic modeling of the small wind turbine generator. Uncertainties of small wind turbine generators are modeled based upon the Weibull distribution functions. That is here f of v equals to k by c into v by c to the power of k minus 1 exponential of minus v by c k minus 1. Here k will be representing for the shape parameter and c for the scale parameter, and v is the wind speed. So this Weibull distribution function, further we can able to make into the cumulative distribution function as given in the equation number 2. So using this, that is collecting the wind data, and then we have to make into the appropriate using the Weibull distribution functions. Then to obtain the power curve of a small wind turbine generator, here as the basic power output of the wind turbine generator is P equals to half rho Cp AV cube. That is we can call that performance coefficient. And then this one rho is the air density, area of the turbine, wind velocity, right? So based upon that complete one, so further we will make into the stochastic modeling. That is turbine performance curve gives the actual wind power output from the wind turbine with the following expression. That is, whenever the wind speed is varying less than the cut-in wind speed, then so the power equals to 0. And whenever the wind speed is within the cut-in wind speed and the rated wind speed, so we can able to use this complete equation. That is A1 into V cube, A2 into V square, A3 into V cube, plus A4 into PR. That is rated power of the turbine. So here, as for my research, I used that 1.5 kilowatt rated wind turbine generator. That rated capacity is going to be multiplied for this complete equation. And A1, A2, A3, A4 are the regression constants of the turbine performance curves. Similarly, other equations also available. That is one, we know that wind turbine. So it always the wind turbine curve will be starting from the stall wind speed, and then cut-in wind speed, then cutout rated wind speed, and cutout wind speeds. So here the time series of wind velocity is used here. That is as we recorded the wind data in our Basaveshwara Engineering College, Bagalkote, using the weather station, and then further using the MATLAB Simulink, so we will be able to find out that the time series of the wind velocity. Then further by using that previous equation, so if we find out that this probability and cumulative distribution functions with wind speed, so here f of v and capital F of v, so we'll use the probability and cumulative distribution function. And here, based upon our Basaveshwara Engineering College location, so we are able to find out that K shape parameter is 2.63 and C scale parameter 5.49. Then stochastic modeling of the loads, that is using the complete complex modeling of the loads, that is A0 plus A1 into VA by V0 plus A2 into VA by V0 whole square, complete into P naught, that is actual voltage VA, nominal voltage of the load V naught, and P naught and Q naught are the nominal real power and reactive power of the loads. So by using this one, stochastic modeling of the load is carried out, and then modeling of the distribution system using open open DSS, that is Open Distribution System Simulator. It is given by the EPRI, Electric Power Research Institute, that is available in the IEEE PES resources. And modeling of the lines mainly at the 3-phase 4-wire line based upon this self impedance of the line, each and every single phase line, and then mutual impedance of the between the lines. That by the using these two equations, it is available even in the many 3-phase power flow textbook also. Then aggregate modeling of SWTG and loads in distribution system. That is here that mainly SWTG is clustered and allocated based on the probability of load generation balance in distribution system. That is, so once if we have the only SWTG and the loads, so we have to aggregate them, and then so we can able to make into connecting into the distribution system. Then only we'll get the efficient SWTG output values. Further developed an aggregated model to combine SWTG and bus loads using the Gaussian distribution methods. There is a random variable x equals to x1, x2, xn into t follows the n dimension Gaussian distribution function. Here x1 we will representing for the small wind turbine generator, and x2 representing for the loads. The aggregated and aggregated probability function is given in following equation. That is here f of wind velocity and the load data is aggregated here. Thus, this first part will be for the completely Weibull distribution function, and second part for the standard distribution function for the loads in the distribution system. Then practical case study. Here, figure 7 describes about the graphical representation of Bessel Engineering College distribution system. That is, I have considered in my research, that is one case study, that is our BC college campus electricity network. In this in this complete representation of a distribution system, you can see that first of all here the HT metering cubicle, that is ESCOM, that is Hubli Electricity Supply Company, sent us the 11 kV power supply to our college campus and receiving at the HT metering cubicle. And further from the HT metering cubicle, so it is distributing into the two feeders. That is one feeder, you can see that red color symbols, that is HT line, and one more this side. That is, these two are the two radial feeders. And then further these two radial feeder will feeding into the separate engineering departments. So our engineering college departments, starting from the one civil engineering department, electrical, mechanical engineering department, their backside we have one distribution transformer center. It is rating of about earlier it is 100 kVA, now it is 400 kVA transformer. So that is a 400 kVA transformer with of voltage rating 11 kV bar 415 volt. So you can see able to see that the primary and secondary distribution transformer center. And then so second in the side you can see that this color symbol, so it is feeding into these three departments. And similarly further 11 kV line is further move on to the another two transformers. So we are calling them as DTC2, DTC3, 100 kV transformer. And these two are feeding into the computer science engineering department and then information and instrumentation technology departments. Further even for the other department also. Further the 11 kV line further move on to the DTC5. It is of rating 63 kVA transformer, and it is feeding to the CPED basic CPED physical education colleges also. And then further 11 kV further move on to the DTC4 of 100 kVA of same voltage rating, and it is feeding into the electronics and communication engineering departments. Then further, so another radial path here, right? So you can able to see it. So DT6 we are named with the same ratings, and it is feeding for the main building, that is classrooms, principal buildings, administration buildings, then hydraulics and transportation, chemistry, basic sciences, biotechnology, industrial production departments. So it is feeding into all And further, we have one more innovative solar wind energy district level energy park, and it is initiated by our guide Dr. Suresh Jangam Shetty, of overall total rating of about 3.1 kilowatt. Here we have uh, uh, solar powered DC irrigation pump sets of about different three power rating, that is 0.5 HP, 1 HP, and 2 HP solar DC irrigation pump sets, and 150 and 500 watt nano wind turbines, about seven types, seven numbers, all connected are the rooftop only. And remaining few of the thermal type of the devices, solar, that is solar dryer, solar installations, and all constituting the solar energy power, solar generation and renewable energy park only. And here we have one more higher rating of 1.5 kilowatt wind turbine generator. It is connected to this DTC 400 kVA transformer only, feeding into the boys hostel, and then further communicating to this our SCADA room. Here we can able to see it SCADA one, and there we have the vertical wind turbine also. Here the horizontal axis wind turbine, and here in the SCADA room we have that able to access the complete communication from the all these seven distribution transformer centers. That is each and every distribution transformer center, that is here you can see that distribution transformer center. So at this distribution transformer center we have the intelligent feeder control unit, that is that IFCU meter. It will be acting like a phasor measuring unit, PMU, usually calling in a industry one. And there in FC meter we have the one digital meter from the this one company, mainly there is the one it will able to access the 52 data from this transformer, so it will be completely the load data only. Then further, so we have the 3 IO module, internet module, and it will be communicating into this nearby the nearby department through this two IP links. So there we have given the one internet protocol address that through the protocol IP, so it will be transferring the complete consumption data into this SCADA room. Similarly, this wind turbine generated data also, it is completely transform the generation information into this SCADA room. So that further, so we will going to converting this complete the BEC distribution system into the single line diagram, that is like this one, that is here modeling of the BEC Bagul-Kote distribution system. That is whatever we have seen that earlier diagram, so that we are able to make that here. So the bus numbers we are going to calling, that is bus number 1 will be the main one receiving at the cubical meter, and the remaining buses are, we are calling them as bus 2 and bus 3, that is LT, HT and LT buses. That is the HT are the main bus of the transformer and LT are the secondary of the transformers. So that the HT bus we are calling it as the higher bus systems, and LT are the low tension side bus systems. So like this one, so at every distribution transformer centers we have the two buses. That at the DTC 1 we have two buses. Similarly, in the college campus we have 7 DTCs. So 7 into 2 buses, so 14 buses, and one will be the main bus will be calling as a 1. So that 1 plus 14, 15 buses are there. That's why we are calling them as calling completely as a 15 bus distribution system. That is here. So 11 kV from the utility main grid, and after that the distribution network we have available here. That is main bus, we are calling it as a first bus, cubical meter 1, that is point of common coupling, where the power is receiving from the utility or grid into our college campus. Then further here we have that, so 2, 3, 4, 5, 6, 7, 8, these are the HT buses, that is 11 kV lines, that is at the high tension side of the distribution transformer centers. And same thing similarly for that is further step down into the power system into the LT side. So calling them as the numbers 9, 10, 11, 12, 13, 14, 15. And load arrows, you can able to see it, department of CV, electrical, mechanical, right? Similar to all the departments. So 3-phase power flow analysis. After connecting the this small wind turbine generator to the one of the buses into the the buses. So we have to conduct the load flow analysis to obtain the complete information of this aggregated model of this wind turbine, small wind turbine generator, and this the load information at the particular centers. So obtain the load, line, load, and bus data of BEC distribution system based on the predecessor and successor method, that is based upon the parent and child load methods. We are going to obtain the complete information of these data. Then modeling of the line, load, and small wind turbine generator are carried out using the open source distribution system simulator software. Conducted the high tension voltage regulation based load flow analysis on BEC distribution system with and without the SWTG. Here HTVR based load flow analysis is my novel outcome of three-phase load flow analysis. That is, as our Basaveshwar Engineering College distribution system, we are recording the power incoming at the chemical meter, and that power is receiving from the nearby distribution centers. That is around 3 kilometer. There we have the 110 kilovolt 1 kilovolt bar 11 kV distribution center located in the Bagalkote district, Karnataka state. So from that one, from 3 kilowatt distribution center to our distribution college campus, so that whichever the loads are available, so that complete is going to be calculated, and accordingly all should be included in our algorithm. So at the point of common coupling, so we have to find out what is the HTVR, and then from that HTVR, so conduct the load flow analysis. So from this one, we will going to calculate what will be the exact voltage at the point of common coupling, and this will be help us to find out that what will be the voltage at the end side of this distribution system. So by that one, we will exactly find out what will be the this voltage at the each and every buses, and even at starting bus till to the end bus also. So these are the two papers we mentioned here. Even few more are available. So from that we'll go to get the complete information. This is the experimental implementation of small wind turbine generator in distribution system. That is here in our college campus. We have the small wind turbine generator here, horizontal axis wind turbine, and this is of the rating of 1.5 kilowatt with the voltage rating of starting from 20 volt variable three-phase AC to up to 110 volt three-phase variable AC. Then we have this rectifier, that is AC to DC converter. That this variable rectifier, this is also one. It will take the three-phase variable AC. You can able to see that here the three inputs R, Y, B, or 1, 2, 3 phase also we can call, and it is incoming, and it is interconnected to this connection terminals. Then from this one, so here we have the full bridge rectifier, and from that one it will converting this variable the AC into the constant 24 volt DC. So that 24 volt DC is available here. That is the plus minus terminals only, and from this terminals, so we are connecting into our battery and charge controllers, and through the charge this 24 volt battery and then charge controllers, further it connected into this grid tie inverters. So this grid tie inverter, it will take about this 24 volt constant DC, 24 volt constant DC, and then it converting into the single phase 230 volt power supply. So that will be connected into connecting into the either into the loads or even into this grid connections also. And then we have the intelligent feeder control unit. So here, L measure instrument we have inside here. That L measure instrument we are able to measure the complete information of the power generation, and then communicating into our SCADA room. So this is our supervisory control and data acquisition center, and here we have server, and through server it will able to access the complete information of the load and generation based upon the IP protocol, that is internet protocol given for each and every location, and accordingly, so we will able to see that what is the data available here, and that data will be available with 24/7 and recording for 5 minutes interval data, so that we can do the data analytics. And here small wind turbine generator is it is procured from the Unitron UV Pune. So from that Unitron 1, so it is of about 1.5 kilowatt. Even this rectifier also from the Unitron only. So this is the window. You can able to set SWTG communication and to the BEC SCADA in Distribution Automation Research Center. And this is the window of the server, our BEC SCADA for Distribution Automation Research Center. That is real-time device monitoring campus distribution SCADA system. And it is developed by the Power Research and Development consultants Bengaluru. And you will see that these are the tools: online analysis, gauge dashboard, digital monitors, data downloads. And here we are given that meter ID 33 numbers for the wind turbine generator 1.5 kilowatt. So recording for the 5 minutes. So it is for the 33 meter ID. Similarly, up to 1 to 32 for different loads, and even the single phase, 3-phase loads are connected to the SCADA centers. Accordingly, names, numbers also given. So results and discussion. To analyze the impact of small wind turbine generator in VC distribution system, fixed point iteration based powerful algorithm has been modeled in OpenDSS. So this is a 3-phase voltage profile of BEC 15 bus distribution system by one DLF method. We can usually call that that is the constant load flow method without the SWTG. And this 4, 8, 11, 13, 15, 16, 10 are the bus numbers, mainly the 3-phase bus numbers only. And this deterministic load flow, we'll be able to see that at the voltage levels, that is y-axis representing for the voltage per units. And the different 3-phase variations are available, and we calling them as medians, different medians. Then 3-phase voltage profiles of BEC distribution system by probabilistic load flow with the SWTG. And with the SWTG, so further voltage are going to be improved at these LT side of the buses. Then comparison of 3-phase voltage profiles of 13th node in BEC 15 bus distribution system without SWTG. That is comparison of the different methods. So here in my research, I took it for this deterministic load flow method, probabilistic load flow method, and experimental connections of this one. So that here deterministic load flow method means, so conducting the load flow, 3-phase load flow for every 10 minutes intervals. That is 10%, 20% up to 100%. And then this probabilistic load flow method means the stochastic modeling, and then taking the probability of this SWTG and load connecting into that particular nodes. That is here 13th node is considered as the one optimal node from one in our college campus, and accordingly we have connected the SWTG at the 13th node, mainly at the R phase. Then comparison of 3-phase voltage profile of 13th node in BEC distribution system with the SWTG. So by this probabilistic method, so voltage profile is improved compared to the previous one, that's starting from even at the 0.985 per units. So nearly it will be improving, and it will be resemble same to the experimental methods also. Then 3-phase voltage profile at 13th bus in BEC distribution system with and without SWTG. That is as here at the R phase of the SWTG is connected, and you can able to see that is mainly at the V1 and V1. That 13th V1 is for the without SWTG. 13th underscore V1 this for the VWTG connection. So slightly the voltage profile is going to be improving at the distribution level sides. And similarly, voltage unbalance factors, that is voltage unbalance factor also improved as for the standards. So that if suppose voltage unbalance factor is less than the 2%, so that will be not considerations. If so, that's why. So SWT is connected to the that is 13th bus. So now based upon this green color symbol, so voltage unbalance factor is slightly reduced. And similarly, so HTVR based distribution system, we consider that is HTVR means, so slightly the voltage sometimes it is reduced, that is 0.98 per unit. So the many literatures are considered that 1 per unit constant, but here we should consider the HTV, that is 0.98. So from that one, so that even the voltage is going to be reduced further. So if it is 0.98 per unit at the PCC, then so what will be the end bus of the distribution systems? So even more, it is going to be reducing. So by connecting the optimal that's SWTG at the particular side, so that voltage profiles can be improved. Comparison of three-phase voltage profile of BC 15 bus distribution system without SWTG. So you can see that. So starting the first table without SWTG. So DLF, PLF method and experimental method. So mainly at the A phase or the R phase we can consider. So the minimum and the maximum the voltage variations able to see here, that is 0.998 per 1 per unit. But at the PLF method, even more we can able to get that the exact the voltage profiles. So it's showing that only 0.99 is near to the 1 per unit, but they don't get the exact voltage profile. But by using the probabilistic load flow method, we'll be able to find out what is that is a 0.9855 per unit voltage profile. And then tables, the one is showing the three-phase voltage profile of BEC distribution system with SWTG. So 0.9855. So now it is improved to the 0.9876 per unit. Then comparison of three-phase voltage profile of BEC distribution system with HTVR. So when if we consider the 0.98 per unit, so we will get that. So even more the improved one, that is the probabilistic load flow method without SWTG with SWTG. So 0.9665 per unit to 0.96783 per unit, and even the maximum the voltage profiles also. Conclusion. Probabilistic load flow analysis with injection of SWTG is carried out at optimal phase in distribution system using fixed point iteration method in OpenDSS. Experimental integration of 1.5 kW SWTG in BEC distribution system is carried out at single phase through grid tie inverter and communicated to BEC SCADA for distribution automation research center. So box plots are reveals the minimum, maximum, and different quartiles of three-phase voltage imbalance factor, power flows, and losses. PLF method shows the 0.967 to 0.98 per unit as 75% quartile, which is near to the experimental verification. At PCC, HTVR had the voltage reduction, but further reduction in voltage at the end nodes due to induction of SWT maintains the voltage imbalance factor within the limits and reduces less than the 2%. Results of PLF is compared with DLF method, where quartiles of different voltage magnitudes are obtained, which is nearer to the experimental investigation. SWTG at optimal location on LT side shows the better improvement in voltage profile with HTVR considerations. PLF method shows the greater accuracy to cater the uncertainties of SWTG in comparison with DLF method. This helps to achieve a practical distribution system into the resilient microgrids. These are the references I referred for my research works. Even many other there, many almost in my research around 130 references are available and not mentioned here. Surely, can anybody contact? I will show you the complete research information references also. Yeah, this is my contact details. Sir.
Participants, if you have any questions, you can type in the chat box so that I can take the questions.
Let me take it from. Okay, so thank you very much for that, Dr. Sangamesh. We have a few questions in the chat, and let me just go ahead and read one of them. So, Saicharan says, microgrid has power fluctuation. So how will this be managed? Any thoughts on that?
Yeah, microgrids are fluctuation. Microgrids have. So can you come again, sir?
Microgrid has power fluctuation. So how it will be managed?
Yeah. Usually in the microgrid side, we will have that this converter side. So based upon this converter and exciters at the main at the point of common coupling, so the voltage exciters will able to maintain that voltage variations. mainly at the usually calling as a this one. Even at the distribution transformer centers also nowadays grid operators they will do. But as for the distribution monitor operators, they have their own separator exciters. So that will based upon the voltage exciters, so we can able to control these fluctuations. Sir, next question, sir. So, or is it fine, sir?
Yeah, fine, sir. More question is there. Are small wind turbines available in market? If so, cost is how much? Else, where it can get it?
So I'm not audible. I'm not getting your voice, sir. What is the question? Is it available in the questions chat box, sir?
No, no. Actually, it is not available. Questions came from Google Form.
Yeah.
Small wind turbines are available in the market. If so, what is the cost of small wind?
Are small wind turbines are available in market? Right, sir? That first question, sir.
So, what is the cost?
Yeah, sir. Actually, as for earlier in 2012-11, we in our college we procured Unitron UV Pune. So there it is showing that in website also is available. Many different ratings. Depend upon the rating wise, we'll have the different facilities. So mainly we can call it 1.5 kilowatt to up to more than 5 to 10 kilowatt turbines. And as for the nowadays, many innovations are came. One I have seen that Avante Garde Innovations, they mentioned that for 1.5 kilowatt, they mentioned that earlier 50,000 rupees cost usually. So even we can search that many will available in the even intent also. But in Unitron, we have purchased it during 2012. So with the complete cost, it's showing that 1.5 lakh rupees, sir, at that time. But nowadays nowadays costs are reduced. That is for the horizontal axis wind turbine, and even we have the vertical axis wind turbine also. So that's also costing 1 to 1.5 lakh, depend upon the company and what the quality they are giving. That is based upon the cut-in wind speed and cut-out wind speeds. So the cut-in wind speed in the market 2.5 to 3.3 meter per second. But for the low wind regime locations, we need the even more lesser cut-in wind speed wind turbine generators. So for that one, so we have to check in the manufacturer cut-in ratings. So based on that one, we can choose for the wind turbine generators also, right? So that even for the 1 meter per second also, it is very the right one, because many locations sometimes during the month of September to up to the February March, so many locations they have the very lesser wind speed. So for that one, so we didn't get the any generations. That's why. So we have to go for the lesser cut-in wind speed, and accordingly the company also they mentioned in their catalog also. Accordingly, the prices also they mention. So for that one Unitron, Power Mitra, Avante Garde Innovations, right? And even our India. So we have the National Institute of Wind Energy Institute. So that is the one main under the MNRE. So they mention what are the manufacturers, wind turbine manufacturers. So we can go through that NIW website, and they mention which are the this small wind turbine generator manufacturers also.
Okay. Thank you.
One more question. The chart box. What is the distance between one and another SWTC? I'm repeating. What is the distance between one and another SWTC?
SWTG.
Yeah.
Distance between.
Yeah.
Actually, as for this one, that concept is mainly for the larger turbines, large wind turbine generators. But for the small wind turbine generators, so we don't have that kind of the work. So as in our college, we have 7 wind turbines, is around 400 watt turbines. So we are connected to depend upon where the loads are available. Mainly for small wind turbine generators, concept is to look into reducing the losses. That is whatever it is generating around very lesser voltage variation, that is 10 to 20 volt low voltage to up to 30 volt, 110 volt variations, 110 volt voltage variations. So that's why to look into the reduction in the losses and then into this voltage reduction. So for that one, so distance is not matter for the small wind turbine generators, I think. Yes, sir.
Okay, I have one more question. So the question, all right, so let me ask mine first. The question is based on the site placement, right, for the SWTG. If we say it's about 1.5 kilowatts, what is the how exactly do we connect this to the distribution grid such that we not lose too much power during
Yes,
that,
sir.
yeah, during the transmission?
Yeah, same thing, sir. We can connect this small wind turbine generator based upon the which phase you wanted to connect. For that one, there are many options. That is, if you have wanted to send it to the grid or consuming that generated energy in local loads only. So for that one, grid tie inverters are available, depend upon your rating and loads also. So that we can go for the this one grid tie inverter. Mainly, I procured for my research Studer make grid tie inverter, so that we can connect this three-phase variable AC converting into the constant AC, then into the single phase AC. So that in the microgrid or distribution system, always we have the three-phase and one neutral wire. So for that one, which phase is the better one, that you have to identify. That is as usual how we are connecting our newly built home. That newly built home is we wanted to connecting into the electricity utility grid. So for that one, the power man can come and he will check that which phase is underloading. So that phase is identifying, and accordingly he will connecting our load into that particular phase. Similarly, small wind turbine generator also we can connecting into that particularly underloaded or higher loaded the phases. So that here I have done the research based upon this particle swarm optimization method. Based upon the particle swarm optimization method, we identify that which bus is the highest priority. That is having that highest priority method. Based on that one, so we identified the here 13th bus in this distribution or BC distribution system, and there we connected this small wind turbine generator, sir.
Thank you very much for that. So in line with that, I think Mayuresh is asking, what are the common problems faced if developed DC is fed into an AC bus system from an SWTG system?
Pardon, sir, I'm not getting your question. Come again, sir.
So he is asking, what are the common problems faced if DC, that's direct current, is fed into an AC bus system from an SWTG?
As for the DC system, here we have that main thing. One main thing is one we can call that usually THD, that's total harmonic distortions. So these harmonics mainly playing at this role. So that we have to look into the factor. That is one thing, and even one more is we have to the problem we are facing is mainly one is this charge controller on the batteries. So we are always, you have to design or we have to plan that battery, right? So what kind of the battery what kind of the voltage battery we require for our distribution system, that we have to design, and accordingly, so we have to go for the connection of the DC generations. So the common problem is mainly this one only. That is, as far I have seen that mainly for this is wind turbine generator only. So usually this will be acting as the DC load into this distribution system only, because starting it is generating AC, then further converting into the DC only. So in the while DC plug into this distribution system, so that time we have faced this voltage variations. That is, as for the three-phase to single phase conversions, we have to look into the what kind of the battery, that is 12 volt battery or 24 volt battery or 48 volt battery we need. So that problems we are arising here mainly. Then afterwards we have this THD. So we have to look into these factors only for the connecting the small wind turbine generator into this distribution system. That is, so usually this all these small wind turbine generators all further they are acting like a DC sources only. Okay, so that's the voltage problems we are facing usually when connecting the DC links DC link into the AC links.
Which
Right, sir?
makes, yeah, thank you. Which makes a whole lot of sense, because if you're going to use the DC systems with the voltage regulations, with the voltage variations, there has to be some system put in place for regulation. The next question now is, how can small wind turbine frameworks, how can SWTG frameworks be used to improve the performance of web applications?
Pardon, come again, sir.
So I think the question is asking, how can SWTG frameworks be used to improve the performance of web applications? I think this is in line with the SCADA system for monitoring and control.
Yeah, sir. Usually, PMS will play the better role for the this web application. Usually, as even we are working on that one also. Earlier, we have weather station procured from virtual hydromet. That is a simple, just like a manual one. It is recording the wind data through this one anemometers, and they connected to the weather station through the wires only. So every 5 minutes or one single minute recording the data, and further we are downloading through this one, means plugging by the one port, one hardware portal only. But nowadays it's come with this one internet protocol, that is through the Zigbee, right? So through the Zigbee, or even the one more we have even also worked on that one, that is through the two some small Zigbee antennas, that is around 200 meters antennas only, so that we can connect that one or the where the anemometer is connected, right? So that Zigbee is, the receiver will be taking that information and sending into this one through the another receiver Zigbee. So they are communicating through this simple IP protocol only. So either as here in our college, we are done the based upon the based upon the IP protocol they given by the server room, or even through the simple if you want to do separate server, so we can make the separate server using those many frameworks are available, web frameworks are available. Mainly this Django framework is very helpful. So that using the Django framework, or even best is a simple we can go for this HTML or PHP sheets only. So that basic PHP sheet or this HTML, so we can make the separate web apps. Okay, so that web apps will be taking this IP locations only, where our wind turbines are connected, and there above the IP locations only, so we can connect the sender Zigbee, so that through that communications will be done, or even through the GPS separate as our mobiles are working, so we can add the separate this one communication SIMs, and accordingly, so this will be also working. Then further we can connecting into the database server, our own server. Otherwise, many nowadays we have this AWS or Google Cloud servers, right? So there I have seen that in the Amazon web services, right? So that AWS they have separate many, so around 10 to 12 frameworks are available. That is either the Linux through, or even the Google Cloud, right? Azure. Otherwise, this even the Django frameworks are available. So from that framework, you can create your own server in the AWS. Otherwise, separate even the low cost, that is just like simple like our GoDaddy servers also available. From that also, you can create our own web applications, sir. So from that, we can download the data and monitor the data also, sir. Is it fine, sir?
Yeah, I think that's fine. You did that very well. Thank you very much for that. So I'm going to try and lump two questions together. The first is, what is the difference between smart grid and normal grids? And with that in mind, what are the future trends in wind turbine technology?
Yeah.
And also, what role would they play?
This is smart grid and even the microgrid. So earlier, the whatever we have the microgrids in this will be calling in 1213 2012 2014. That time this word came. So microgrids means earlier the different the local loads are connecting. That is where the power sources are minimal or remote locations. So that data that power the scarcity is available. So they are locally they're locally generating the data, they're generating the power and consuming there only. But for the smart microgrid, here we have to communicate the different sources, that is different distributed energy resources. Suppose here we have a small wind turbine generator, and further we have the this one solar photovoltaic, right? And then further we have some locations they have even more many things, that is this one nowadays the hydrogen fuels or even from the local generations, and we can connect the battery sources, right? And then we can connect this one diesel generators also. All together should be working together. That is, it should be communicated with respect to the grid and into these DERs, so that one intelligent device should be working in the microgrid so that it can able to give the power generation to the local load based upon the priority. That is, if we have the solar photovoltaic and wind turbine generator, so the first priority that intelligent algorithm should take the energy from this renewable energy sources only. If suppose those two renewable energy sources are not available, then second priority should be given to the logic should be given to this available battery sources, and next into this any other resources like diesel generators through the inverters, right? If suppose it not available, then we can go for this grid utility systems, so that this intelligent algorithm should be working in the localizer that distribution system only. So we can call them as a smart microgrids. That is for the one we can call smart microgrid centers.
Yeah.
And nowadays, even many engineering colleges and even the hospital systems or the shopping malls or the military sectors, they have their own distribution centers and also the communication centers also. And even though this sugar industries, we can call them as cogeneration system, they have also the automation systems, so that they can generate their own energy and communicate all those generations using this intelligent architectures, so that we can call them as a smart microgrids. Is that sufficient, sir?
Yes, yes, it does. Thank you very much. So our next question, so hold on, everyone. I think we have 4 minutes left to go, so let's try and be fast with this. We have 2 more questions. The first one says, can SWTG systems be able to compete even on a per basis if compared to solar panel based generator? So that would be in terms of the generating capacity, in terms of size,
Yes, sir.
and all of that, sir.
Usually, yeah. First question is coming nowadays. It is that is competition between the wind turbine generator, small wind turbine generator, and the solar photovoltaic, sir. Actually, solar photovoltaic nowadays it is booming and having many advantages compared to this one. Many pros and cons are there compared to the wind turbine generator, because there we get that there is no rotating part in the solar photovoltaic, but in the wind turbine generators we have the rotating parts. But as for the one concerned, I have worked in the SWTG and even the solar photovoltaic, so that once if the solar photovoltaic, if it is damaged through the any things, but that is by accidentally or by intentionally someone, if it damages solar panels, then so it should be completely remove the panel and bring the new one only, and it can't be locally remanufacture or bring that one into the original state. So we should procure the new panel only. But in the small wind turbine generators or the wind turbine generators, so we can able to rebuild that wind turbine generators as it this small wind turbine generator, the blades also we can able to manufacture. Even I have manufactured this 1.5 kilowatt WTG blade using this resin gel coat cobalt acid by the help of this training given by the NIWE, National Institute of Wind Energy Wind Turbine Generating Institute. So they conducted the training, and I have gone through that one, and I have built the horizontal axis wind turbine generator and even the vertical axis wind turbine generator also. So that if you have the training, sufficient training to the local guys, that is mainly diploma or ITI guys, or even the local vendor, those who are repairing this irrigation pump sets or mixer grinder pumps, this one machines, motors only. So if they know the knowledge, similarly, so they can rebuild the turbines if that it's a damaged one, so that you can be able to once again we can come into the original state as compared to the solar photovoltaic. Even the solar photovoltaic nowadays for the 1 watt is around 30 to 33, 35 rupees per watt, but that is for the panel only. But even for the going for the even further the installation, further accessories and the inverters, so the cost will be more or less it is equivalent to the small wind turbine generator only. So that is as for the in our Indian cost nowadays government giving, it is around 70,000 rupees to 1 lakh rupees for the 1 kilowatt for SPV, solar photovoltaic. Similarly, for small wind turbine generator also, for means wind turbine generator turbine generators, and even for the accessory like this one, inverters and all. But if you are good enough to build the turbine, so we can build it around the 30 to 40,000 rupees only. As that one website I have seen, that Avante Garde Innovations, they built the small wind turbine generator for showing that they're in website. I have seen that for 1 kilowatt 50,000 rupees earlier they charge. I have seen that one, but nowadays I don't know what they're making the prices. So this is the some of the advantages, sir. Many pros and cons for between the WTG and even the SPV also.
Right. Thank you very much. So while we wait for the feedback link to be posted, and I know is our 1 hour is now up. Let's just quickly squeeze in one last question, if you don't mind, Dr. Sangamesh.
Yes, sir. Yes, sir. No issue, sir.
All right, thank you. So, two questions here. What role do microgrids play during a power outage? But before that, there's a previous question, which was a follow-up to the question of web frameworks. And the question here is there any alternative way to access the data if the servers are busy?
Alternative way to access the data, wind data.
Yes, if servers are busy.
Yeah. So mainly one website is that niwe.res.nic.in. NIWE, as for the Indian MNRE Institute. So NIWE website will give the charge basis wind data. Otherwise, we can go for the NREL laboratory website or Global Wind Atlas, right? And many like that one we have. But as for the one, I have seen that in a researcher. So this wind data usually, so we need that location basis. So as for the location basis, the data, right? So this will be usually we have that separate weather station, and even the wind mast also connected on our college campus. So that is procured from this virtual hydromet, right? So we can procure that one and we can connect the wind anemometer and wind mast, so we can get the wind data. Otherwise, we can go for this free website like NREL, Global Wind Atlas, right? And even the NASA also giving the this based upon the this longitude and latitude one. If you're connecting in that one, so you can able to get the free wind data also. But we didn't get the exact one because as for the researcher one, we have to go for the stochastic wind data or time series wind data, at least for the 15 minutes of wind interval. So for that one, at least we should have the separate wind weather stations. In our Basaveshwar Engineering College, Bagalkot, we have 2 weather stations from the virtual hydromet and wind mast. Okay, so like that one, we can get the data. Otherwise, you can go for the NIWE website. They will provide the wind data.
All right. So for the other question on microgrids and power outage.
Yeah.
So what role do microgrids play during power outage, and how how would an SWTG help in managing grid resilience during
Yeah.
power outage?
Yeah, during the power outage, same thing. The concept is the name itself only calling that microgrid means it should work that intelligent should be working that. So once if the power goes off or turned off, then in the power outage timing. So our renewable energy sources should be able to work on that, act upon that one, and accordingly switch on, and it feed the energy from these wind turbine generators only. That is there's a renewable energy sources only. That is, if we have the sufficient solar PV and SWTG on our rooftop, so that we can get the in the day timing, so both are going to be working, and accordingly they will feed the energy into that local loads. If suppose those two are not available, then our batteries are store the energies, right? So that during the night time, so wind turbine generator are working, and even the batteries also they are sufficient to feed the local loads. That's why the name itself only microgrid or your smart grid, right? The concept is only that microgrid means it is a set of the interconnection of the loads and the local loads and this distributed energy resources. So that there we have that sufficient intelligent the one device. That device should logically operate whenever the load or turn on this one load outages are or the power outage situation comes. Then so these are going to be happen like a just like a regularly our educational institutes have this diesel generators. Similarly, this renewable energy source also should work as like a this diesel generators only. So then only we can call it as a this resilient microgrid, sir. So one of the
Oh,
questions I'm seeing that in the chat box. So is it able to connecting at the our residential home buildings? Yes, sir. Surely, sir. Nowadays, it is a many already installed. Even in our college campus, 10 years back only we installed this 400 watt wind turbines on the this engineering college building only. It is a 2-floor building only. So it is of about 1.5 sorry 400 watt capacity and voltage rating around that is 20 volt AC to up to 110 volt AC. It's varying, and there only we have the this one rectifier. So it is giving the 12 volt output. So all these 7 type rooftop wind turbines, they're giving this one, this power output, and even we are connecting this hybrid solar also. That is about 150 watt 6 turbines. So that is around 900 watt solar PV and 2400 watt 2400 watt WTG. Both are connected in hybrid, and each and every turbine we have one 500 watt 500 volt ampere inverter. So they are sufficiently working, and only the issue is facing is this battery. So as for the battery, earlier we have um, this one lead acid distilled battery. So every 3 to 4 months we have to look into that battery management by adding the distilled water and all. That is the only challenging things in the renewable energy sources. Otherwise, so it is best one as like a wind turbines are connecting. Similarly, we are connecting into the grid also. So one more question: what type of the battery is connecting into the grid? So as for we are facing the many issues in the lead acid battery one, but nowadays lithium ion batteries are came, and they are the best one for the one, and even the nickel cadmium batteries also, the sealed battery, or even lesser price like lead acid sealed batteries are came. So that also we can use it for the this SWTG and SPV hybrid one for the rooftop conditions.
thank you very much for all the questions. Thank you very much, Dr. Sangamesh, for your time. Over to you, Madhu.
Yeah. Thank you very much, sir, for your active participation. So thank you very much for all the participants who actively participated in this webinar and posted very interesting questions. I think the title is full-fledged right now because most of the questions came from the participants regarding the title of this webinar. So
Yes,
it's take my privilege to say a lot of thanks. Thank you very much for giving this conducting of this PSYP. So first of all, I would like to say thank you to the PSYP chair, Alvin Paul, and Dr. Jinjao, my technical activities subcommittee coordinator, and my all technical team, especially Belagan, for cooperating this webinar. And thank you very much for Dr. Sangamesh sir for accepting our request for delivering this webinar. And thank you very much for Swarnandhra College of Engineering Technology Management for giving this valuable permission to conduct this gathering in virtual mode. And also thank Suresh Kumar sir, principal of Swarnandhra College of Engineering Technology, who is the backbone of our IEEE Swarnandhra student branch. He always encourages us to conduct a step of collaborative activities for the upliftment of the knowledge to the student community. And finally, but not the least, I thank very much to all the participants who actively participated and shown their interest to attend this webinar. Thank you very much for all the participants. Thank you very much, sir. Thank you, sir. Thank you very much for accepting our request.
Yeah. Thank you, sir. Thank you for all this one, sir.
Yes, you can fill the feedback form which is available in the chat box. Again, please. Participants, you can fill this feedback. Thank you, sir. Thank you, sir.
Yeah, thank you very much, sir. So can I exit, sir?
Yes, sir. Yes, sir.
Okay. Thank you very much, sir.
I will send you my appreciation letter to you through email, sir. Thank you very much, sir.
Yeah, sir. Yeah, sir. Thank you, sir.
Thank you.
Yes, sir. Thank you. Bye, sir.